In the last lecture, we have learned about elementary Quotient groups. So elementary Quotient groups are those Quotient groups which has a finite orbit in the upper half plane union its boundary at infinity. So our next goal is to find Quotient groups which are non-elementary. So by that, what we mean? So every orbit is infinite. So a Quotient group, it acts on hyperbolic plane, and our goal is to find Quotient groups such that every orbit is infinite. So for example, if I take PSL to Z, so it is a discrete subgroup of PSL to R. So this is an example of non-elementary Quotient group. So our next goal is to find non-elementary Quotient group. So what will prove that if I take a closed orientable surface of genus greater than equals to 2, so its fundamental group will be a non-elementary Quotient group. So now to understand this fundamental group of surfaces, so first we need to define surfaces. So in this lecture, we'll define surface and also give classification of surface. So let us begin. Yeah. So let us first go through the definition of surface. So you start with a topological space S. So that is said to be a surface if that is a Hausdorff space, if it is second countable means it has a countable basis, it is connected, and for each point of this surface S, there exists an open set U such that, so that point is contained in that open set, and that open set U is homeomorphic to an open subset of R2. Yeah. So if it is locally homeomorphic to R2, so then we call that to be a surface. So this is my definition of surface. And now, what do you mean by surface with boundary? So a topological space is said to be surface with boundary. Again, that space, I'll take it to be Hausdorff, connected, second countable. And now for each point X of this set S, so either there exists an open set which is homeomorphic to an open subset of R2, or so this U, so this is homeomorphic to a semi-disk in R2. So by semi-disk, so what do we mean? So you take this part of x-axis, let us take an open interval, and let us take a disk. So semi-disk means this thing. So here this upper boundary of the semi-disk, it is not there. So this lower boundary, it is included in this semi-disk. So this is the definition of the semi-disk in R2. Yeah. So if an open subset of S, if it is homeomorphic to an open subset of R2, or U is homeomorphic to semi-disk in R2, so then we call that surface to be with, so that space to be surface with boundary. So now let us come to example. So you take unit sphere. So what we are going to prove that this unit sphere, so this is unit sphere in R3, so this is a surface. So yeah, so for each point we need to find an open set which is homeomorphic to an open subset of R2. So what is the standard procedure to prove the sphere is a surface? Use this stereographic projection. So let us take this U to be this S2 minus north pole, N is 0, 0, 1. And now you take the stereographic projection. So what is stereographic projection? So you take X bar to be a point in U, and you take a straight line starting from this N. So the straight line, it passes through X bar, and it will intersect the plane Z equals to 0 at some point. It will meet the XY plane. So this is my XY plane at some point. So that point I have called it to be Rx. So R is the map taking X bar to this point, Rx bar. So this is called the stereographic projection. So this is called the stereographic projection. And one can prove that this R, in fact, it is a homeomorphism from U to your R2. And now you take similarly V to be the sphere minus the south pole. South pole is 0, 0, minus 1. And again, you have a map from V to R2. Again, you take the stereographic projection. So now note that, so this U and B, it covers S2, means S2 is equal to U union B. So if I take any point, P belongs to S2, either it lies in U or B, and U and B homomorphic to R2. So therefore, we have proved that this sphere, it is a surface. And what is an example of surface with boundary? So you take this cylinder. So this is nothing but S1 cross this closed interval. So now if I take this point, so if I take this point X here, so then around this point you can get an open neighborhood of this point X. So U, such that U is homeomorphic to an open subset of R2. And now if I take any point, so in this thing, so let us take S1 cross minus 1, means this circle. And if I take any point here, so there exists an open neighborhood of that point. So this one, so this is homeomorphic to, so this semidisk. So therefore cylinder, so this is a surface with two boundary components. Okay, so now let me define genus of a surface. So what do you mean by genus n surfaces? That we are going to define. So we are going to define it inductively. So for n equals to 0, means genus is 0. The surface is defined to be just the sphere, unit sphere. This is my surface. It doesn't have any genus. And now just n equals to 1. So what we do? So n equals to 1. So what we do? So we take a cylinder. So we take a cylinder and attach that cylinder to the sphere in the following way. Yeah, maybe I'll first draw a picture here. So you take a sphere, and now what you do, so you make two holes, means, so you take two open disk in the sphere and take it out from the sphere. So it will create a two hole, and now you take a cylinder. Suppose So, so when you take out the open disk from the sphere, so you'll get a circle, and here also you'll get a circle C2. And now let us call the one boundary component of this cylinder to be C1 prime and another to be your C2 prime. So now what you do? So you attach this C1 prime to C1 and C2 prime to your C2. So C1 and C1 prime, so they are homeomorphic to circle. You can attach by a homeomorphism. So the resulting thing, suppose your homeomorphism is orientation preserving. So then, so what you'll get here essentially this figure. So a handle is attached on a sphere. And so this is again homeomorphic to your torus. So this is again homeomorphic to your torus. So that is the thing it is written here. So first of all, so let us understand what you mean by handle. So by a handle, so what we mean, so it is just a homeomorphic copy of a cylinder. Yeah. So when I said about sphere, so when you make two holes means you take two open discs, disjoint open disc in the sphere and take it out from the sphere. So it again, so this will be homeomorphic to a cylinder. So note that. So this will be again. So this is again homeomorphic to the cylinder. So topologically, it is again a cylinder. Okay. So attaching one handle to sphere means, so we are attaching two handles on their boundary components. Okay. So we have two handles here. So this is one handle and this is another handle. So this lower one, you can just consider it to be a sphere with two holes. Okay. So now we can attach this thing in two ways. So one is the following. So C1 and C1 prime. So these are the boundary. So these two boundary components. C1 is the boundary component, one boundary component of this lower handle, and C1 prime, it is the boundary component of the upper handle. So you attach C1 to C1 prime just by the identity map. So just by the identity map you attach. And also, so C2 and C2 prime are the other boundary components. So you attach C2 to C2 prime by just identity map. So C2 and C2 prime, so they are circles, homeomorphic to circles. You can just take it to be circle. And you attach C2 to C2 prime just by identity map. So what picture you will get? So you'll get this picture. So you'll get this thing. So this is torus. So by attaching one handle to sphere, so we get torus. Now, so this one of this attaching map, you can take it to be orientation reversing. Yeah. So here, so again you are attaching two, you are attaching one handle to sphere. So the lower one, so this is sphere with two holes. And the upper one is homeomorphic to cylinder. So that is your a handle. So here, so you are attaching C1 to C1 prime again by identity map. So attach C1 to C1 prime by identity map. And now here, yeah, so that thing I have written it here. So C1 to C1 prime, what is the map? So e to the power it goes to e to the power it. So that is my map. So that is an identity map. So we attach C1 to C1 prime using the entity map. And now here you attach C2 to C2 prime with the help of this map. E to the power it goes to e to the power minus it. So here the attaching map is the following. So phi of eit is e to the power minus eit. So now note that here, so if I take this point, if I take this point in C2 prime, so this point is identified to this other side of this C2. So because of, so this map phi is here, it is an orientation reversing map. Yeah. So now, so the picture, it will be different here from the torus. So what will be this picture? So we are attaching this C2 prime to this C2 in a different way, not the identity map. So we will get this picture here. So essentially, so what we will get here, the client's portal. So this is a non-orientable surface. So this is a non-orientable surface. And for n equals to 2, so you continue the process. So now, okay, so for n equals to 2, so what we are going to do, so you take sphere. So this is my sphere with 4 holes. So D1 union D2 union D3 union D4. So Di is homeomorphic to we can say, you can take this open ball. So you can, Di is homeomorphic to this thing, and they are disjoint with each other. So Di intersection Dj is empty for all I not equal to j. So so on the sphere you make 4 holes, and now again, so you attach 2 handles. So one here and another one here. So if you attach, so if the attaching maps are your orientation preserving, so you'll get a surface which is an orientable surface. So here I have attached, so here the attaching maps are orientation preserving homeomorphisms. So I'll get a surface. So this, I'll again get a surface which is homeomorphic to this picture. So this, I'll call it to be genus 2 orientable surface. So genus 2 means, so we are attaching 2 handles to the spheres. So similarly, we can have non-orientable surface of genus 2. So that I'm not drawing it here. And for n equals to k, again, you can attach k handles to spheres. So similarly, we can have genus n or non-orientable surface. Okay, and now let us make it little rigorous. I mean, how to define the surface, how to get the surface as a quotient space. So for that, we should know the definition of this quotient topology. So what do you mean by quotient topology? So let X be a topological space and Y be a set. And let us take a surjective map from X to Y. And on Y, you want to define a topology such that with respect to that, this F is continuous. So the obvious way is the following. So you take all those collection B in all those collection of subsets of Y such that inverse image of those subsets are open in X. So B subset of Y such that F inverse B belongs to your top. So this collection, it forms a topology in Y, and this topology is called to be quotient topology. And under this topology, so this F, it is a continuous map. And now let us take a topological space and suppose, so this is an equivalence relation. Suppose you have an equivalence relation on this topological space X. So you'll have a quotient map from this X to this quotient space. So on this quotient space, you can put the quotient topology such that this map Q, it is continuous. So this Q, it will be a continuous map. So on this quotient space, you put quotient topology. Okay, for example, so if I take this square, and now you identify the opposite sides. So this is my square. So this bottom side is identified as the upper side, or in other way, so we can define an equivalence relation on this square. So S comma 0 is identified with S comma 1, and for this sides, this vertical sides, so 0t is identified with 1t. So you can define this relation on the space X, and the quotient space is, one can check that this is homeomorphic to torus. So I'm sure that this you have learned in the topology course earlier. So you start with a unit square and you identify the opposite sides to get a torus. So as a surface of revolution, so this is the equation of torus. So this also you can write down. So this equation, so you take this map F from this square to your R3. So this is my map. So F is defined to be like this. So this thing, so this definition of this F. So this, how do you get this thing? So you take R3 and you take a circle of radius small r, and center of that circle lies on this x-axis, and distance of that center to origin is capital R. And now what you do, so you rotate about, so this z-axis. So we'll get the round torus. Yeah, so this T2, I'll call it to be this round torus. Yeah, so X again is the unit square. So we have a map from X to this torus. And yeah, so if we want to prove that this quotient space is homeomorphic to torus, so this is the way. So you have a map from X to torus, and you have a quotient map Q from X to this quotient space. So there will be a natural map, a bar from this quotient space to this torus. So one can prove that, so this a bar, in fact, it is a homeomorphism. So this, in fact, it is a homeomorphism. Yeah, so that thing I have written it here. And this torus also you can write as S1 cross S1. So again, one can prove that this S1 cross S1, it is homeomorphic to your torus. Yeah. So again, so we have this map. So G from this X is this unit squared. So you have a map from G to S1 cross S1. So again, so there exists a continuous map G bar from the quotient space to S1 cross S1 such that G bar compose the quotient map is equal to your G. So again, one can prove that this G bar, it is a homeomorphism. So therefore, the quotient space, so this quotient space is homeomorphic to torus, and also S1 cross S1 is homeomorphic to torus. Okay, so this part already we have seen this thing. So this is not, I'm not repeating this thing. Another important concept is connected sum. So this again I'll be coming. So for that thing, so let me say something. So let us take two topological space X and Y, and let us take A to be a subspace of X and B to be a subspace of Y. And suppose there exists a homeomorphism phi from A to B. And let us take this disjoint union of X and Y. So what we are going to do, so we want to build a space from X and Y by attaching A to B. So what is the way to do that thing? So now on this disjoint union, so define a relation. So what is the definition of this relation? So A is related to your phi A. So A is related to your phi A. So that is my relation. And now you take this quotient space. So this is the obvious way of doing this thing. So here is the picture. So this is my space X. And this is my space A. So we have a map from A to B. So that map is phi. So you have this map. And now what you do, so you take a point from this set A and you take this point phi A. So A is related to your phi A. That is the thing. So we have this quotient space here and you put the quotient topology. So this space, I'll denote it like this. So this map phi, it is called the attaching map. So for example, if I take X to be a cylinder, Y is also a copy of the cylinder. And so A you can take to be C1 union C2 and B to be C1 prime union C2 prime. What is the map phi? Phi is coming from this identity map. So identity map, it takes C1 to C1 prime and identity map takes C2 to C2 prime. So the space, so the phi is the attaching map. So here phi is equal to identity. So the space what you will get is just the torus. And now, so here, so yeah, so this also earlier we have discussed. So instead of taking here this identity map, if I take the orientation, so here if I take it to be orientation reversing, so then the space, so this will be Klein spot. So that is the thing, it is written here. So this I am not again repeating. So now what is the definition of this connected sum? So let us take two surfaces S1 and S2 and Di be an open set in Si such that Di is homeomorphic to an open disk in R2. Yeah, so this is my picture. And the closure of Di bar, so it is just the closed disk. Now what you do? So take out this open disk from this Si. So Si minus di. So I is equal to 1 and 2. And also note that this del di, it is the boundary, topological boundary of this di. So here boundary means topological boundary. So del di, it is the topological boundary of di. I is equal to 1, 2. So this boundary is homeomorphic to circle. Okay, so for example, if I take S1 to be torus, S2 to be torus. So from torus, I'll take out this open disk. So then it will be a torus with one boundary component, and I'll get another copy of this thing. Okay. And now what you do, so you attach this del d1 to del d2 by a homeomorphism. So that is the thing it is written here. So this is called the connected sum. So this phi, it is the homeomorphism from del d1 to del d2, and you attach this torus to this torus. I mean torus with boundary component, this boundary, one boundary component, and this torus is with this boundary component. So you attach the boundary component to get this connected sum. So this is nothing but a genus 2 surface. So for any genus n surface, you can repeat this process. Yeah. So you can repeat this process. So this is torus connected sum, torus connected sum, torus connected sum, torus. So k times connected sum torus. So we'll get genus k plus 1 surface. Okay. So now let me define what you mean by Mobius strip. So you start with a unit square. So you start with the unit square, and now, so what you do, so this point t comma 0, so this point t comma 0, so this is identified to this point 1 minus t comma 1, so this point. So here is the recipe of the identification. So the quotient space, so this quotient space, so what you will get is the Mobius strip. So one can prove that, so this Mobius strip has one boundary component. So cylinder has two boundary components, and Mobius strip, it has one boundary component. And so if you know the notion of orientability, so this Mobius strip, it is a non-orientable surface. Okay, so we can take another definition of non-orientability. So a surface is not orientable if it contains a Mobius strip. Otherwise, it is called to be orientable. So, so here what I have proved that if I take Klein's bottle, so and if I take, so Klein's bottle is, and again, so this Klein's bottle, you can identify it in this way. So you take the square, so you take the square, so 0s point is identified with 1s, and t comma 0 is identified with 1 minus t comma 1. So the identification is only on the boundary of the square. So if you take the quotient space, you will get the Klein's bottle. And now here, if I take this rectangle, so take this rectangle, so this is, yeah, this one. So this point is 1/3 comma 0, and this interval ends at 2 by 3 comma 0. So if I take this rectangle, so this is a Mobius strip. So Mobius strip is included in this client's portal. So therefore, this client's portal, it is a non-orientable surface. So now what is the classification theorem of closed surface? So first of all, what do you mean by closed surface? So a surface S is said to be closed if S is compact and does not have any boundaries. So boundary here means topological boundary. So a surface is closed if it is compact and without boundary. So what is the classification of orientable closed surfaces? So any closed orientable surface is homeomorphic to one of this. So either it is a sphere, means genus 0 surface, torus, genus 1 surface, genus 2 means torus connected some torus, and it can be genus G surface. So this is about the classification of orientable closed surface. And what about non-orientable closed surface? Okay. So to have a classification of non-orientable closed surface, so first we have to understand what you mean by real projective plane. So you take a unit disk with its boundary, and yeah, you have identification only on its boundary. So this x comma y point is identified with minus x comma minus y. So if x square plus y square is equal to 1, so only identification is on the boundary only. So this x comma y, it lies in the S1 unit circle. So therefore minus x minus y, it will lie also on the unit circle. So you can define an equivalence relation on this disk. So xy is related with minus x comma minus y. So the quotient space, will call it to be RP2. And again, one can prove that this RP2, it is a surface. And again, one can show that it is a non-orientable surface. Also, so you can prove this exercise. So client's portal is nothing but RP2 connected some RP2. So what is the classification theorem here for the non-orientable closed surface? So any closed non-orientable surface is homomorphic to one of this. So either it is RP2 or RP2 connected some RP2, which means it is a client's portal, or k times connected sum of this RP2. So this is the classification theorem. Okay, so this is all about the surface. And in some lecture, we'll learn about the fundamental group of surface.